So thanks for coming to my talk. Title was already just described, so let's begin. So a little bit about me. I'm a principal engineer at Lightbend. I am a member of the Fast Data Platform team, which is a team that's building a stack of software, sort of like Cloudera or Hortonworks does for big data. We do something similar for streaming platforms. So we have a number of stream processors we support, like Spark and Flink, Akka Streams, Kafka Streams, and then like the underlying infrastructure like Kafka and Kubernetes or DCOS. I specialize in the Kafka ecosystem on this team. So as a result of that, I contribute to various projects within that ecosystem, including Kafka itself. So the Kafka Streams, Scala DSL, I was a part of getting that into Apache Kafka. Alpakka Kafka itself, which was formerly known as Reactive Kafka. I've made a number of contributions there. Streamsy is a Kafka on Kubernetes operator-based implementation, which I've been involved with a lot this year. And DCOS Commons is just a library to help run stateful workloads on DCOS. And it's used as part of DCOS Kafka to run Kafka on DCOS and Apache Mesos. So Alpakka is an open source initiative, and it's a initiative to integrate disparate systems together. So it's a container project. It doesn't really have its own code. It has some documentation. Maybe it'll have some code of its own in the future, but it's really just bringing together a bunch of connectors to integrate various systems with Akka Streams to help build these stream-aware reactive pipelines in Java or Scala. So it's a very similar technology to Apache Camel or Kafka Connect, if you're familiar with those, but it's not configuration-based, it's not a framework. All these connectors are available as just library dependencies, so you include them in a program as you would any other dependency in your POM XML or your build SBT. So here's kind of a logo cloud of some of the connectors that are supported. I put them into three categories here: the cloud services, data stores, and messaging. So for cloud services, there's support for AWS S3, SQS, DynamoDB, PubSub on Google Cloud, and then most of the popular data stores that you've heard of, we have connectors for those as well. And of course, messaging. So MQTT is a new, well, there was an existing contribution. There's a new one that looks really promising that just came out. AMQP implementations like RabbitMQ, JMS implementations, and then of course Kafka itself. So the Alpakka Kafka connector is obviously used to connect Kafka to Akka Streams. It was formerly known as Akka Streams Kafka briefly for about a year, and then before that it was known as Reactive Kafka, which most people probably know it as, who've been using it for a while. And it actually predates the Alpakka community initiative by a number of years. It was started by a company called Software Mill, and it was identified early on by the Akka team as a really promising project to integrate with Kafka. So they brought it in-house to the Akka GitHub organization and iterated on it, made it even better. So it's used by a lot of people in the Scala ecosystem. It's used by a lot of Lightbend clients in production. We provide support for it. And it's used internally in a bunch of Lightbend projects too, including Legom, which is our microservice framework. So it's used as an optional plugin for communicating between microservices. It's also used in a commercial product called Fast Data Pipelines, which will be talked about in early next year and hopefully get its first release in Q1 next year. And it's bundled. So it's used by a lot of people in production today, and but people might not have heard about it as much, or at least not lately. So I wanted to do this presentation to talk more about it. So some of the things that Akka Streams brings to the table are things like backpressure, which we're going to talk about in the next couple slides. So stream processors today, like Spark and Flink, they do things like massive, they support massive volume, massive aggregations across like lots of different servers really well. They have a lot of good streaming semantics, but they don't support backpressure. And that's one of its defining attributes of Akka Streams. Akka Streams was originally created to make streaming semantics easier within an Akka actor system. So if you're familiar with Akka, your basic components are your Akka actors, the messages that they send between each other asynchronously. And you can obviously model any kind of communication you want with those components, but modeling complex streaming semantics can be difficult. So Akka Streams was created to make that easier, to provide like kind of a consistent implementation of these semantics, and can be used internally within an actor system, but it can also be brought into any old JVM project and used by itself. You don't need to know anything about Akka actors to start using it. And of course, it's using actors under the hood, but that's transparent to the end user, unless you start implementing more advanced features of it. So here's a basic pipeline. Each one of these components, you need at least a source and a sink, obviously. A source has one outlet, sink at least one outlet, a sink has at least one inlet, and then you have this arbitrary number of flows in between. And messages obviously flow downstream from the source to the sink, but you also have this other channel that's going upstream. And this is for the backpressure protocol in Akka Streams, which we'll talk about in the next slide. Another unique feature of Akka Streams is that it can support really complex graphs. So most of the popular stream processors only support acyclic graphs, which means you can't have cycles or loops within your graph. But Akka Streams actually supports this if you have a need for that. I haven't seen a lot of systems that do that, but if you need to implement some sort of feedback loop where a downstream flow influences an upstream flow, for example, you can do that if you want. The Akka Streams is built, the backpressure within Akka Streams is implemented using this specification called Reactive Streams. And this provides asynchronous stream processing with non-blocking backpressure. And it borrows a lot of the same principles you would find in the Reactive Manifesto to help build flexible, loosely coupled, scalable systems that communicate asynchronously. And the spec itself was spearheaded by Lightbend, but it has contributions from a lot of companies in the streaming space, that a lot of household names like Red Hat, Netflix, and Pivotal have all contributed towards this spec. And so Akka Streams is a JVM implementation of it. There's other implementations out there that run on the JVM, and you can also implement it on another language runtime if you want. I believe there's a couple examples out there. This is just an example of 3. And what this slide is calling out is that the Reactive Streams spec was actually introduced into JDK 9 under this package and a set of types under this package. And the names aren't exactly the same as what the spec defines, but they're semantically equivalent. And this is cool because each one of these libraries implements their own implementation of Reactive Streams. But once the community moves past Java 8, probably once people start using Java 11 a lot, we'll start seeing releases of these guys that can do away with their own internal implementation and use the flow implementation in the JDK, and that will reduce some boilerplate, obviously, and also make it easier to interoperate between these. So this is a short slide demo of how backpressure works. So I've been referring to these as components. I'm going to use the actual name, which is a graph stage within Akka Streams. So a graph stage can be a source, can be a flow, can be a sink, and it has a lot of the same characteristics as an actor in Akka. it has a mailbox, which is represented by these rectangles underneath. And in Akka, by default, if your mailbox is unconstrained in size, it can be very large, which can present problems. You can imagine that if a actor is not processing messages fast enough, those mailboxes can eventually fill with messages and you can run out of memory. In Akka Streams, they actually constrain the size by default. And this is what helps enable backpressure to actually function. So let's start with the example. Oh, the other thing I forgot to mention is that like Akka actors, they also only process one message at a time. And in order to achieve concurrency, you basically scale out instances of these. And this is really good because it's one of the core features of Akka to provide a easy way to model concurrency. So common problems in concurrent systems are closing over code that multiple threads could access and changing state that can introduce race conditions, things like that. You don't get that in Akka actors because you have that guarantee you're processing one message at a time, and it can mutate state within that actor as much as it likes because it knows nothing else is closing over it at the same time. It's called the single-threaded illusion in Akka, and you get the same thing in a flow, and then in a graph stage, and then you can also encapsulate state within these graph stages as well. So back when you start an Akka stream, the most downstream components, like the sink, are the first that act. No messages are passing through until those downstream components start requesting messages. So in this case, the sink says or requires messages. It doesn't have any in its mailbox. It's ready to receive them. So it sends this demand request upstream using that channel I showed on an earlier slide. And it sends it to its immediate upstream graph stage, so the flow. The flow doesn't have any messages to provide it, so it sends its own message upstream to the source, and then the source does what it does and loads those messages from somewhere. So in this example, a Kafka topic. And then now it can start satisfying those demand requests that were made previously. So the flow will start getting messages and processing output that it can now deliver to the sink because it knows the sink is waiting for messages too. Another principle of backpressure and why we're actually doing backpressure is because we don't want to overflow graph stages downstream or systems downstream. It doesn't have to be within the same JVM. So to simplify how this works, I just have two graph stages. So in this case, the flow says, I can handle some messages now. And in a naive implementation of a pull model, you might think that it would send a demand request for every message that it needs, but you can imagine that doesn't scale. If you have millions of messages going through this pipeline, this graph, then obviously you have a million demand requests too. So that doesn't scale very well. So the compromise is this dynamic push-pull model that we have in Reactive Streams. So the flow knows exactly how many messages it can accommodate because it knows the size of this mailbox. It's bounded in size. So it says, in this case, it's the size of 5. You can tune this, of course. And it sends a demand request with that metadata in it, that it can handle up to 5. And this is sort of the pull side of that model. And then the source can immediately satisfy that by batch sending or pushing 5 messages. And you can see that as these demand requests get larger in size, that there's less overhead going on that back channel, the backpressure channel, which help with performance. And the whole point of doing all this is that we want to solve this problem. The common problem in streaming is that we have a fast producer, a slow consumer, and this is a good way of solving that problem. So this use case would never happen because when the flow is at capacity, it would start backpressuring, and it would never receive another message from the source until until it has room and sends those demand requests. So this is a simple kind of end-to-end Akka Streams example. Everything you need is here except the import, so I can fit it on the slide. But you basically have your Akka actor system that you spin up because it's using actors under the hood. You give it a name, you have a materializer to instantiate the actors. And then this example is just very simple. It's just a small iterable, in-memory iterable going from 1 to 100 and calculating factorials. And this scan is a graph stage. This is a stateful graph stage, sort of like a fold, but instead of folding to completion, which we might not have a completion in a streaming use case, obviously, it will emit its state or whatever you want after every iteration. And then this is being formatted and put into a sink, which in this case is just a file. So why would you use Alpakka Kafka? We talked about backpressure, complex event processing I'll get into later on in this presentation. It's a really good solution for that. And then if you need to model really complex graphs that may have cycles in them, for example, it's also a good choice. So here's a Alpakka Kafka program end-to-end. So in this case, all the examples are going to be consuming in this presentation. All the examples will be consuming from Kafka and then producing back to Kafka. So a consume, transform, produce workflow. And when you bring Alpakka Kafka into your project, you're basically getting a library of sources and sinks and flows, and then some other types in order for to work with these sources and sinks and flows. So this is a committable source, which is basically using offset committing within Kafka, which we'll talk about shortly. It's sending messages downstream along with some metadata about where those messages came from, what offset they are, and so on. A simple topic subscription of where the messages are coming from. Really naive transformation, which is actually not really doing anything except passing that message along. And then a sync, which is basically producing it to the subscription found here and committing that they were read. The messages we consumed were read. And this is just some extra boilerplate to gracefully shut down that stream, to stop the source, drain all the outstanding messages, and wait for everything to be completed in the sync before shutting down a program. So I'm going to talk about a couple Kafka features in a little more detail in order to better illustrate why or how you use certain features in Alpakka Kafka. So consumer groups is first. So consumer groups are how we handle, how we scale up our consumers efficiently so that they can handle more messages. So the common use case when we don't have enough processing power on the consumer side is we start seeing this attribute of consumer lag. And it can be represented in tools. This is a Kafka offset monitor. And this blue line is representing the latest messages, latest offset available in the topics we're consuming, or an aggregate of them anyway. And then this, I think it's green. This line represents the latest offset that we've read in that consumer group. And you can see they're growing over time. And this is a bad situation to be in. Ideally, they would start approaching, they would be very close to one another. But when they grow like this, if they grow indefinitely, then you have a problem. Eventually, your consumers are reading later and later data, and eventually Kafka, which is the buffer holding all these messages in between, is going to start evicting data because it's going to run out of disk eventually. So you need to handle this situation. And we'll see how to do that in a second. But what you want to see is these lines converging and that your lag approaches zero. So you have very few messages between these two. So this is the same thing represented as a diagram. So you have producers with a combined throughput of 10 megabytes a second, for example, and then the consumers can only process at 9 megabytes a second. So you get this growing lag over time. And then there's no back pressure, so we can't tell producers to slow down. And we don't want to, because in a lot of, like, the use case for Kafka is to absorb a lot of volume and to, kind of prevent that volume from cascading into our internal infrastructure that might not be able to handle it. Or at least that's what a lot of people use Kafka for. So there's no way to tell these producers to slow down. So we handle this by adding another consumer, and then the aggregate throughput of our consumer now could reach 12 megabytes a second, and eventually that lag will fix itself over time. So what's happening when we add a consumer or remove a consumer is called a rebalance of the consumer group. So consumers or members of the consumer group all receive unique partitions, so they're not processing the same data twice. Rebalances happen when you add a client, remove it. If the topic itself changes, more partitions are added to it, for example. So in this case, we'll just add a client. The client comes along, it has the same group ID, and it communicates with Kafka's consumer group coordinator. So it says, I want to join this group. The group coordinator talks to the leader of the consumer group, which is usually the oldest member of that group. And it has some logic in it to determine how to reassign partitions efficiently across this group. So there's some default strategies that most people use within Kafka, but if you have a need to implement your own, you can do it in the client, which is why this exists in the client and not in Kafka itself, so that users have the option of extending that and easily without having to update the cluster, for example. So the leader sends a new client to partition assignment back to the coordinator, which sends it back out to the clients. But before they start consuming, there's a hook where they have an opportunity to do something with the partitions that they were assigned and the partitions they no longer have that have been revoked and balanced to another client. And a common thing they do is actually commit the offsets they have for those revoked partitions. So the messages they have kind of in flight that they're processing, oftentimes you want to finish processing them and then commit them to the offset log within Kafka. Once that's done, then they continue reading from the consumer group with their new partition assignment. And how that's done so in this slide, these hooks are available in the Kafka client. They're event handlers to handle when partitions are revoked and assigned. So in Alpakka Kafka, we support that with this rebalance listener, which can be any Akka actor. You don't have to create a new one just for the job. It could be an existing one. It could be in the same JVM, and it could be a remote Akka actor. And it just needs to handle these two messages. And then this is showing the example where we want to commit those messages from the partitions that have been revoked, so that the next client that receives that partition can read from the latest offset. We don't have duplication going on. So you get a reference to this actor and you pass it along with your topic subscription when you spin up your stream. That's everything I just said. Transactions. So this is the meat of this presentation. I think a lot of people, they've probably heard of consumer group balancing and all that, but they might not be familiar with the transactional systems available in Kafka now. So we'll spend some time talking about that. So transactions enable atomic writes across multiple Kafka topics and partitions. It was introduced as part of Kafka 0.11 last year, June 28th. And it wasn't possible before that because there were situations where there are corner cases where a producer could send duplicate messages or send messages out of order for various reasons I don't have time to get into. So Kafka Transactions is actually a number of features implemented in order to provide really good message delivery guarantees in Kafka. So people familiar with messaging systems should be familiar with these, but just a refresher at most once is basically I want the latest data now. I don't really care if there's gaps in the data. I just want to process data as fast as possible. Good example of this is like a game client, a game server that's using the UDP protocol. It doesn't have all these strict kind of acknowledgement requirements built into the protocol itself. So you can model that in Kafka if you have a need. At least once is what I find most people settle on. They want to process every message at least once. And this is basically waiting for acknowledgements that messages were received by the producer before they move on. And if they don't receive those acknowledgements, then they retry. So the consequence is that it's possible you can have duplicate messages, which is why it's called at least once. And then exactly once is sort of this holy grail of message delivery guarantees that theoretically isn't possible at a low protocol level. You can provide those guarantees with TCP. Can do at least once. UDP is good at most once, but there's no way to guarantee exactly once, which is basically that messages are sent to their destination once, processed only once, sent in the order sent in the correct order. You can't provide all these guarantees because you require more context at a higher level of the network stack than a lower level can provide. So the way it's done in Kafka is by faking certain, we're basically faking exactly once by implementing a couple features. So I like to call it at least once message delivery with effective item potency guarantees on the sink. So we'll do things like retry until we get acknowledgements from the sink. We have an item potent source, so the Kafka is doing deduping for us somehow. And we enforce that messages are not processed more than once and that they are sent in the right order. So the way that this is implemented within Kafka is three main features: the item potent producer, multiple partition atomic writes, and consumer read isolation level. So we'll go through each one of these quickly. This is probably the easiest one to understand. It's just, in this example, we have a client sending a message along with some metadata, a sequence number, which is just an increasing number from 0, and you have one of these sequence numbers per partition that you're producing to, and then a producer ID that gets generated for a session of this producer. So it sends its message, the broker persists it to a partition, and then it sends an acknowledgement back to the client. And if this can't succeed for whatever reason, then naturally the client's going to retry, and when it retries, it sends the same information again. But the broker is expecting a new message with an incremented sequence number of 1, and so, but it knows that it already persisted this one. So instead of failing, it just sends an acknowledgement saying to the client, hey, we already received this message. It's a duplicate, but carry on and give us the next message. If the broker was sent a sequence number of like 2, and we've only received 0, then that's a fatal exception, and basically the stream will shut down at that point. We can't recover from that. We can't provide those message order guarantees anymore because something went seriously wrong. The atomic writes are used to, as part of the commit process in Kafka Transactions. So when you commit a transaction, you're basically kicking off an implementation of the two-phase commit protocol, which people should be familiar with if you've worked with distributed systems. So how that's working in Kafka is that the first phase is just preparing the commit. So all the messages, all the data we want as a part of this transaction's been persisted where we want it. And then the second phase is this actual atomic operation where we write to various partitions all at the same time, one or nothing, or all or nothing kind of operation. So we commit these control messages to the partitions we're producing to, and these are messages that are transparent to the end user. They're just handled by the brokers and the clients, and we'll see why they're used in a sec. But they basically say, everything before this offset has been part of a successful transaction. transaction log is updated with a successful transaction message. And then all of the messages we were consuming to transform and produce to another Kafka topic are committed. So we're basically saying everything we consumed is part of this transaction has also been committed. So this is happening all at once. And this naturally flows into the last thing, which is the read isolation level. So you have these clients reading the output of those transactional workloads, and you don't want them to process messages as fast as possible. You only want them to process messages that are part of a successful transaction. So it's when you set this isolation level in your client to read committed, it's basically waiting until it sees a control message before it consumes any of those previous offsets. So guaranteeing, those guarantees of the transaction are effective. And this should illustrate that there's a problem with transactional workloads. So when they implemented this, they did some benchmarking with a standard Kafka application and a transactional one. And even though there's a lot of overhead in this kind of system, they didn't notice really much of a degradation in performance. The penalty comes with the end-to-end latency. So if you have multiple transactional workloads here, the fact that you are now batching a series of records as part of a transaction is what causes end-to-end latency within your pipeline. So if you have a lot of these in serial sequentially like this, the ones farther downstream are going to have a longer latency just because of the fact of these batches. So that's something to watch out for when building systems with this. So the way this is implemented in Alpakka Kafka is there's a sink. So there's a transactional source, which doesn't really do much. It's kind of similar to the committable source. And then all the magic is in the transactional sink. And there's also a transactional flow. And it's basically committing all the messages as part of the transaction every interval. So it's using 100 milliseconds by default. And the design of this is very similar to how Kafka Streams does it itself. They use the same default, actually. And it commits every interval. So I'm just going to show a little slide demo how that works. So when we start, we begin a transaction. And while the transaction's open, we got messages flowing through the system. They're added to the mailbox. They get processed successfully. We have acknowledgements that these are part of the transaction. Sorry, they're produced to the target topic partitions. We have some other messages waiting for an acknowledgement that they've been persisted. And everything's good. We keep receiving messages for a while, and then this loop ticks. So the commit interval elapses at 100 milliseconds elapses, and instead of doing something immediately within Akka, the way it works is in order to give that single-threaded illusion where we're only processing one message at a time, the timer will actually send like this meta message into our own mailbox, and we append that to the mailbox. And then once that message is processed, it kicks off a bunch of things. So the first thing is it starts backpressuring. It stops sending demand requests because we can't add more messages to the transaction until it's committed. So it does that. And then we start committing the transaction. So we send all the consumed offsets, all these messages that were, all the consumed messages that transformed into these messages that are part of our transaction are read. And then we can actually commit the transaction. One thing I didn't show is when we do a commit, we have to drain these messages waiting for an acknowledgement. So we wait for all of those to become part of the transaction. We commit the transaction, and once that's complete, then the system starts working again. We start sending demand requests. We're not backpressuring anymore, and things continue as they did before. So here's the code in Alpakka Kafka to do that. It's almost identical to what we had before in the previous example. The only difference is we have another source, another sink, we have a transactional ID. But this demonstrates how easy it is for the end user. So although what's happening under the hood is fairly complex, for an end user it's pretty easy to get started with transactions. And it's reducing a lot of extra boilerplate you'd have to otherwise write to get these guarantees, like deduping logic and message ordering logic and things like that. So complex event processing is used to take an event or a message of some kind, do some sort of complex analysis of it. So I just have a little slide, or a slide here that's demonstrating how that's done in Akka Streams. We use something called the ask pattern, which is basically a way to model a request and response workflow asynchronously. And the ask pattern is used to communicate with other Akka actor systems. And then it asynchronously waits for a response or time set. So you can use this to talk to another actor within the actor system that the stream's running in, or it could be a remote actor in its own system. And it could also be part of an Akka cluster. So it could be spilled over across multiple machines. And you can model like any kind of complex business logic you can imagine within Akka. So this shows how easy it is to communicate with actor systems using Akka Streams. This is the code in what's happening in that previous slide. So we have this actor here. It's receiving some kind of message, processing it by probably creating more messages, sending them throughout the actor system or across Akka cluster. It's implemented in Scala using the question mark as part of the Scala DSL. And one property that's important is this parallelism factor. So a map async is basically doing things concurrently, but maintains message order within Akka Streams. But in order to keep this efficient, we want to have a parallelism factor of at least greater than 1, so that the actor always has like a message waiting in its mailbox that it can quickly dequeue and process efficiently. Persistent stateful stages are really useful to recover state after failure, create an event log for auditing purposes, or to share state, probably more importantly. So this is a big part of CQRS, and event sourcing is a subpattern of that. If you have a lot of writes and you want to share that stateful information that those writes are creating in an efficient way, then you'll use this pattern, event sourcing, most likely. Lots of databases implement it. Kafka Streams, K-tables implement it. So here's a really kind of convoluted diagram of how that might work, where you get these requests in, commands or queries are handled by a request handler, which emits an event. And then that event gets handled by the persistence plugin for Akka, which puts it into an event log, which is a append-only event log. It also gets handled by the event handler, which is maintaining the state or enriching the event with stateful information. And that's how it works in normal operation. And then the recovery phase is, like, if it's recovering from failure, we don't consume any messages until we replay this full event log through this workflow again, which reconstitutes the state and brings it back to what we want. So unfortunately, this isn't a concrete implementation yet in Akka Streams. There is a proposal for doing it by Martin Krasser. I'm hoping there's an enterprising individual in this crowd that might pick it up, because it would be a really cool contribution to make to Akka Streams, and it would be fun to work on, I think, as well. So that's it. I'm going to close with this release notes from the latest Alpakka Kafka release. It was released as of November 6th, a couple weeks ago. It's using the new asynchronous client APIs. That's probably the most notable change. But I wanted to also demonstrate that it's an active project, lots of user contributions, has its own team at Lightbend as well. So it gets a lot of attention. And I'll conclude with saying that I hope that I've done a good job in showing different parts of the Akka toolkit. It's just one tool. as part of, it's just one tool in the tool belt. All these tools are kind of lying on the floor, ready for you to pick them up and use them. And I hope you consider using them to build your next streaming platform. So thanks, and I'll take some questions if we have some time. No time? Okay. Thank you.